Okay. Thank you very much for coming. It's time to start our traditional NIA CFD seminar, and today actually a kick-off meeting for the fall season. It maybe doesn't feel like a new beginning because we had the last meeting of the spring season maybe just 2 weeks ago, but today is really new beginning, and to make it exciting, our speaker today is our own Hiro Nishikawa. He definitely doesn't need introduction in this audience, but for our larger online audience, so it's, Hiro is a graduate of the famous CFD school from the University of Michigan. He joined NIA in 2007, and he is associate fellow here at NIA. Hiro is very passionate about CFD. He has a book, and he has very useful notes that I find extremely illuminating and useful in my own research. And in past several years, Hiro is very much involved in developing of new discretization methods that use some hyperbolic principles. And those methods promise significant improvements in accuracy of the solutions, and specifically of accuracy of derived quantities for the solution, and also some significant convergence acceleration. So today's talk is first, second, and third order hyperbolic Navier-Stokes solvers, and here is Hiro Nishikawa.
Thank you, Boris. Thank you very much for coming and watching. This work has been funded by our research office, and support from Software Cradle is greatly acknowledged. So today, I'm going to talk about myth. The myth is everywhere. Sometimes it is a creepy story like urban legend, and sometimes it is a scientific myth. And a popular example is the 5-second rule. Food dropped on the floor. It's safe to eat if picked up within 5 seconds. Right? And some people believe it, and others don't. And that's the nature of myths. And CFD is no exception. There are myths in CFD. Here's myth number 1. Nice and smooth viscous grid. Boundary layer grid must be smooth and orthogonal. Some people believe it. And it makes the grid generation very hard for complex geometries. And grid adaptation inside boundary layer can be very difficult. But there are other people who claim that, who don't really believe this. And they can use triangles and text and highly skewed, stretched. So this is a myth. But the biggest myth I've ever heard is this one, the myth number 2, impossible high-order scheme. It says there exists a third-order scheme that is less expensive, cheaper, on a given grid than second-order finite-volume scheme widely used in practical CFD codes today. It's impossible, because on a given grid, to get third-order accuracy, you have to do something. It's extra work, so it cannot be cheap. But there are people who really believe this. Yes, there exists such a third-order scheme. So it sounds like very much like a myth. So in this talk, we are going to investigate these CFD myths. But actually, it's not we. They are going to investigate. There are experts in investigating myths. So this talk is going to be a myth-buster talk, and they are experts. And as always, they always say, don't try this at home. It may be dangerous to do it at home. Okay. So they looked at this impossible high-order scheme myth, and of course, Jamie Hyman, that sounds impossible. Yes, it does. But I agree with Adam Savage that nothing is impossible. It only takes a crazy idea to make it possible. But they have no idea what this crazy idea can do. So they go online and search in Google. The keywords are fast convergence, Navier-Stokes, accurate, and radical. And then, top of the list comes up this paper, PDF file, new generation hyperbolic Navier-Stokes. It sounds crazy. So they click on this and write up this paper. And I'm so glad they come to this paper because this is my paper. So I know, but this is, I know this is crazy. Navier-Stokes cannot be hyperbolic, the viscous terms. And although 1/8 speed up, that's crazy because the speed up factor is not just a constant. H is a mesh spacing. So as you refine the mesh, it gets faster and faster. And accurate viscous heat fluxes, we'll see what it means. But I know this very well. This is the method I've been pursuing since 2007, starting from diffusion. But in 2011, this is described in this AIW paper 3 years ago. I was able to extend it to Navier-Stokes system. So on the left, this is a traditional Navier-Stokes system. The continuity and the momentum and energy. And tau is the viscous stress and Q is the heat flux. And this mu, VH, are scaled viscosity. So this Navier-Stokes has viscous term, which has second derivatives, because this goes in here and this goes in here, differentiated once again. But hyperbolic Navier-Stokes system that I propose is this one on the right. It has exactly the same continuity, momentum, and energy equations, but it has additional equations. The evolution equation for the viscous stress and heat flux. And this construction is based on this. The two systems are designed to be equivalent in the steady state. Or, if you simply drop the time derivatives, these two equations are exactly the same. Okay. So, so in this talk, I will focus on the steady problem to solve this to get a steady solution for Navier-Stokes. But unsteady computation is possible. I'm so glad that I took this and extended this to unsteady schemes. And we have 2 papers already using implicit time stepping. And within each physical time step, we use the steady solver developed based on this hyperbolic formulation. And I will focus on the compressible Navier-Stokes, but incompressible Navier-Stokes system can also formulate as a hyperbolic system, and which is in the paper. This talk will focus on the compressible Navier-Stokes. One of the problems I noticed when I made this system was that this relaxation time, T, the viscous relaxation and heating relaxation, basically these are 3 parameters, because once to reach the steady state, these 2 coefficients can be anything. But these times depend on the viscosities, so it's non-linear. And this whole system cannot be written as a conservative system. But we can put these coefficients to the left-hand side of the time derivative, because we don't care about the time accuracy. So we can write this as a precondition conservative system. This is 1D, but this is possible for 2D and 3D. And to construct a numerical scheme, we need eigenstructure of this whole system, which is still difficult. I still cannot find eigenvalue for the whole system. But if we split up Jacobian, this is a precondition Jacobian. We can split this into implicit part and viscous part. And the implicit part is just the Euler equation, so we know everything. And viscous part can be analyzed. I can get eigenvalues, eigenvectors, everything. And then, that's the implicit part. And then I found this viscous term, hyperbolic system, is really hyperbolic. And it represents the pair of weights, the viscous stress weight and the heating weight. They are symmetric. It always comes with a pair. So it's a symmetric weight. And zero eigenvalue comes from the fact that continuity equation doesn't have viscous term. So the Navier-Stokes has hyperbolic implicit and hyperbolic viscous. So all we need are methods for hyperbolic system. Yeah.
So if there were a bulk viscosity, that zero would become a third wave, third pair of waves?
Bulk viscosity.
Bulk viscosity would not be a
No.
continuity equation.
This is...
It's that there's zero viscous terms in the continuity equation. The bulk viscosity is still going to affect the momentum equations.
Yes,
and
not...
the energy equation.
Okay.
Yeah, this is...
If you have species transport equations.
Species transport would have it, yeah, and then that's a whole other list of
Well,
things.
that's another continuity.
Yeah.
Right. Yeah. So continuity doesn't have viscous term. When I did this analysis, I could throw out continue the equations. But anyway, so upwind viscous scheme, right? Sounds crazy, and he loves it. So if this is true, Jamie said there's a good chance to confirm the means. And actually, there are many advantages that have been demonstrated in the past. The first of all, because the viscous term is now hyperbolic, schemes and techniques, whatever developed for out-of-edge or hyperbolic system, can be directly applied to viscous terms. Multidimensional upwind, high order, limiters, anything. And the most of all, I think this is important. The first order viscous scheme can be constructed now. The first order viscous scheme usually doesn't make sense because if you have second derivative viscous term, and if you have first order scheme, but the quantity you're interested in viscous field simulation is the viscous stresses and heat fluxes, those derivatives. If you have first order ideal solution, no matter what you do, I think it's very difficult to get a gradient that has all the property. It is typically one order less. So first order scheme, and you get zeroth order gradient on irregular range. But this first order viscous scheme makes sense for hyperbolic because viscous stress and heat fluxes, they are variables. And we obtain primitive variables and these derivatives to the same order values. And the robustness, like implicit scheme, whenever you have a problem, you turn off the gradient, go back to first order upwind. And that is found to be very robust. You can do the same for the viscous term if you need. And consistent Jacobian, when you construct the implicit scheme on the Jacobian side, typically for the implicit term, you differentiate the first order compact upwind scheme. And you can do the same for the viscous scheme. And if you work on DG, you can construct easily the P0 viscous scheme. And in P multiplicated, you can go down to P0 with no problem. And also the 1 over h acceleration in convergence because there are no second derivatives anymore. And it gives for explicit schemes for steady problems, you can use order h times that instead of order h squared. And also for implicit scheme, the linear system has a much reduced condition number 1 over h instead of 1 over h squared. And it does speed up the relaxation scheme. And the speed up factor is 1 over h. It's not 2 times, 3 times. It's much faster on refined view. And high order derivatives, typical viscous stress and heat fluxes for Navier-Stokes. The same order accuracy for solution derivatives can be obtained on irregular mesh. And not just more accurate, but it gives highly smooth derivatives. I will show some results on skewed irregular mesh. So, as I always say, if you have a good implicit scheme, you have a very good viscous scheme. So, let's try it. So, let's discretize it by a finite volume scheme, because that's a very popular discretization method used in a practice CFD code, NASA fancy software cradle, tetra VLR code, etc. So that's the target equation. That's hyperbolic Navier-Stokes with rotary precondition conservative system with source term. We focus on the triangular grid, but we take a dual control volume and integrate this conservation law over dual volume. The flux is computed at the midpoint and multiplied by the directed area, and we end up with this spatial discretization. This is multiplied by local preconditioning, and for the time being, this source term has been discretized by point integration. This should be okay for first and second order. And numerical flux is upward, but it's, like I said, this is difficult. So I don't know the whole eigenstructure. So I'll show in the next slide how to construct this upward flux. And accuracy basically depends on how you get the left and right states. If you just use nodal values, you get first order scheme. Or linearly extrapolated to the midpoint, you get second order accuracy. And the important point here is that first, second order for both implicit and viscous terms. When I say first order scheme, it is first order scheme for everything. the numerical flux is actually simple. Like many people do. You have implicit flux, you add viscous flux. The only difference is my viscous flux is upwind. So in this part, I use both flux and upwind viscous. I construct the dissipation term this way, but there's nothing new here. If you are familiar with local pretension technique, this is how you construct the dissipation term. But basically, you have to construct dissipation based on the preconditioned wave system, so P times AN. But you have to multiply P inverse because at the end, the residual will be multiplied from the left by the P. So to cancel this line. So it looks right. So, but this is not third order arcade. We are investigating third order arcade scheme myth. So, but we can actually make it third order very quickly. This is a big discovery by Katz and Sankara, basically 2011. They discovered this edge-based finite volume scheme achieves third order accuracy by a set of minor modifications on triangular and tetrahedral grids. This is a special property on these two grids. So we still do the linear extrapolation to the midpoint, but the gradient now needs to be computed to the second order accuracy on irregular mesh, which means we need to use quadratic fit, not the linear. And also extrapolate flux also, as well as the solution, to the midpoint. That said, these two modifications will make this edge-based scheme third order accurate. But this is not trivial for viscous and source terms. Actually, Katz and Sankara, they extended this to the viscous scheme, viscous terms. It requires a little bit more work. It requires third order gradient. It requires cubic fit. But if you use hyperbolic Navier-Stokes system, because this viscous term is now hyperbolic, you can apply the same third order scheme of implicit and viscous terms. But there is a source term. And Katz actually found a special formula for the source term discretization. But I also found another way to achieve this. So what can we do with the source term? We stay crazy, make it hyperbolic. So this idea was published in JCP 2012. We can write this S is a source term. Write this as a divergence form. In the divergence for F, S, and GS are some flux. So that this whole divergence form will approximate this source term. And actually, you can find, this is one choice. You can define Fx flux in this way. It requires gradient and second derivative of the source term. But you can set the G0. I needed this high order term because when you plug this back into this divergence form and differentiate, you will find the resulting expression will be S plus third order error term. So this should be sufficient for the third order finite volume. So now I rewrite this hyperbolic Navier-Stokes in this way. There's no source term anymore. So everything is hyperbolic. But actually, if you analyze the Jacobian, this is hyperbolic because S depends on the solution. So the residual looks like this. There's no source term in integration here. The source term is now incorporated into the flux computation. Yeah.
So you're requiring some kind of continuity or some properties on the source term, right? So it needs to be two-time differentiable.
Oh, yeah. Yes.
Is that always possible?
I don't think so.
The source term in the vicinity of the shock, though. I mean, there's an implicit assumption here again of continuity of C to continuity, and yet crossing the shock, you don't have that.
Across the shock, I don't know if I can retain third order accuracy in other terms.
Well, I'm even worried about just plain accuracy. That term, I need to think about it a little bit.
Yeah, I know.
I'm concerned about there being a large error associated with an implicit assumption that the source term is continuous across the shock. I mean, we see that all
You
the
don't
time.
need to use this modification across the shock. You can
Right.
just use the first order.
Right.
The source doesn't need to be modified across the shock.
Yeah.
If you don't want third order, just use whatever.
Yeah, if you
point with.
ignore this, then this approximation is accurate up to second order. And
And
if you ignore this
then
term,
you have to have a scheme then which identifies this is a shock.
typically you do that for the
Well, it's
invisible.
not shock fitting, but you have to at least identify that this is something that I want to draw down.
Yeah.
And they're, yeah, okay.
Mm. But actually, it is possible to formulate this so that I don't need second derivatives. That's what I'm right now working on. Yes, if possible, it's nice to eliminate these second derivatives. I think it's possible. So numerical flux for Navier-Stokes has now three parts: the implicit upwind flux plus upwind viscous flux plus upwind source time. If you don't like upwind scheme, this is too much for you. But it is simple. Everything discretized in the same scheme. So for implicit scheme, if you detect shock and you want to go back to the first order scheme, you do the same for all the terms. The same mechanism applied to all the terms. And so now I construct an implicit solver. The residual at the node, I completely drop the time derivative. So the residual for the first and second order has this point integration. But third order, there's no point integration, it's in the flux form. And I'd like to point out, now I drop the time derivatives. These residuals are consistent with the original Navier-Stokes equation. Okay, because time derivative is gone. This is a way to discretize the original Navier-Stokes. I start from hyperbolic system, but once discretized, I can come back to the original Navier-Stokes. So the discrete solutions that satisfy these residual equations are a solution to the Navier-Stokes equation. Okay. So I have a global system of residual equation, and this is an implicit update. The correction is a solution to the linearized system. And the Jacobian is exact for first order scheme. So I have Newton's method for the first order. It converges to machine zero within 10 iterations. And to solve this linear system, I just for simplicity, Gauss-Seidel relaxation. And I just reduce the linear residual by one order, and then I can move on. And for the second and third order scheme, I typically run first order scheme to get some good initial solution. This is very fast. In the convergence plot, you will not see any data for the first order run. And the boundary conditions. I have mixed weak and strong boundary condition. For the weak boundary condition, basically integrate. I close the residual by the boundary contribution across this place and across this place. And this formula is known for a long time, decades, that this 5/6 times this center node and 1/6 times the flux here. This formula is very important to preserve second order accuracy at the boundary node. And then to compute this flux, we specify the right side by its physical condition. And there's a good paper on this boundary procedure. I just learned from that paper. For strong condition, the wall, basically viscous wall, I use strong condition. I strongly impose zero velocity. There's no particular reason that I use this, but you can do this in a weak formulation. And also adiabatic condition. This is actually a normal problem, but it's like a Numerical problem because I carry these variables, so I can specify this directly at the node, boundary node. And the viscous stress is predicted by the scheme by solving the residual equation at the boundary node.
One question.
Yes.
Since you introduce a new variable, shouldn't that be part of your boundary condition or initial condition also? In a sense, you'll always have a mixed kind, whereas you say only UV is 0. But ideally, you should also specify the gradients because those are your new unknowns which you use to make it hyperbolic.
No, typically, you specify either solution or derivative.
I know, but that's in a typical sense. In your case, your derivative is not actually a derivative, it's a new variable. It's not exactly, if it were a derivative.
No, but you still do the same. And this is a more complicated case, but for diffusion, you can actually check the discretized problem is well posed. If you specify both variables, that's over-specified. You cannot solve it. So either you specify the solution at the boundary or derivative at the boundary. But the derivative is a variable. So I just use this variable and specify. Yeah. And also remember, these discrete equations are consistent with original Navier-Stokes.
It's time derivative added, so you may need additional initial conditions, but not additional boundary conditions.
But it slows down when I try this. But the failure is always an option. I think it's always an option in research. And I performed some analysis. I can't show the details here. I'm still working on this paper. But what I found from the Fourier analysis on the regular grid, it does slow down the downside relaxation. The convergence rate becomes just 1 for high aspect ratio. But also the analysis shows that if I modify this length scale in the relaxation time, if I put aspect ratio in the denominator, it will improve the convergence. So that way I was able to run this scheme. But again, another problem. It's not very accurate on the boundary. And he knows where. This second order boundary quadrature that I talked about, 5, 6, and 1, 6. It doesn't work for third order scheme, and we need to derive a new formula. And we did. So this doesn't work for third order scheme. This is a new formula. That paper is actually currently in review. Sometime soon, I'd like to give a seminar on this one. This is also another very interesting story. But I found this, it does make a huge difference. So this is test problem results from the diffusion scheme on this is a derivative, the solution on the boundary. And black curve is the exact solution, and the blue ones are obtained with the new formula. And the red one obtained with the second order formula. It decreases the accuracy considerably. So this is very important on the boundary. So now it's working and verified accuracy. So accuracy identification in a square domain irregular grid, and Mach number 0.3, some parameters there. And I compare this hyperbolic scheme with a conventional scheme. Conventional scheme has the same raw flux and alpha damping scheme, some least square based viscous scheme, second order accurate. So these are the primitive variables, the errors in the L1 norm. So the density, the red curves are the hyperbolic results, and the blue is the conventional scheme. So we see first and second and third order accurate in the density, and conventional scheme is second order. And the same for other variables, X velocity, Y velocity, and pressure. These are not very interesting, just as expected. The interesting part is this viscous stresses, the derivatives on those irregular mesh. The tau x and tau xy and tau yy. These are velocity, basically the gradients, which is always typically one order lower for the conventional scheme. So you see this blue from conventional scheme is only first order accurate. But Hyperbolic Navier-Stokes achieve first and second and third order for all variables. This one a little bit less than first order. Same story for the heat flux, Qx and Qy. We have first, second, third order for both components, but for conventional, it's one first order accurate, one order lower. It's very difficult to get the same order of accuracy for the gradient. And actually, I'm very interested in velocity gradients because they are very useful for many purposes, like vorticity prediction, and they can be used in the turbulence models. And actually, That's a difficult problem. I'll show you. So I have first, second, third order tau xx, tau xy, tau yy, 3 equations. But the velocity component are gradients, ux, uy, vx, vy, 4 coordinates. I cannot solve. Okay. Not enough equation. This comes from the symmetry of the viscous stress tensor. But if you look at the equation on the left, tau xx and tau yy, those 2 equations, they involve only ux and vy. So I can solve for these 2 components. So if I have first, second, third order viscous stress, I can get ux and vy to the same order of accuracy. And that's shown here. This is ux, first, second, third, and then vy, first, second, third. But look at the equation in the middle. That involves uy and vx, and 1 equation. I can get these 2. So what I came up with to get high order accuracy was, this was interesting. If you differentiate these 3 equations with respect to x and y, you end up with 6 equations. And second derivative of the velocity components, there are 6 components. So I can invert. So I was able to get second derivative of the velocity to the one of the lower accuracy, because these are gradients. And by using these second derivatives, I can do quadratic least squares on a linear least squares tensor, because the curvature term is given. That's how I got these 2 results, uy and vx. But it looks like a first, second, third in the beginning, but as I refine the mesh, yeah, it's 0th order, first order, and second order. It's very difficult to get the same order of accuracy. But actually, this 2D case is actually very special. In 3D, all components will be one or the lower. I cannot solve even for AUX and VY because of the Stokes hypothesis. So this requires a new approach, and that's what I'm working on right now in order to get first, second, third order velocity gradients. But anyway, we can now try some realistic problem in a simple case like bump flow. The Mach 0.3, the Lorentz number 100, and the 3 different grids, but these grids are highly irregular and stretched and skewed. It's not a typical grid, so like he says, it's too skewed and we have a better grid. But this is the chance to investigate this number 1. The boundary layer grid, does it have to be smooth and also? These are some results. This is the vorticity contours. This is conventional. It may be hard to see, but these contours are irregular. On the second order hyperbolic, it's actually better, and even better for the third order. But this is not genuinely third order accurate, second order accurate. It's just very accurate first and second order. The interesting thing is this one, skin friction on the wall, the viscous stress. This is a distribution here to blow up. You can easily see the conventional scheme gives oscillations. And this is actually typical on highly irregular triangle mesh. But Hyperbolic Navier-Stokes gives much smoother grid. And it's hard to guess what kind of grid was used. It's so smooth. Yeah, that's very nice, but how about the cost? And you don't believe this. On the finest mesh, the coarser mesh is hard to see here, but on the finest mesh, the conventional scheme is this one, the black one. And second order hyperbolic Navier-Stokes is much faster. And even third order hyperbolic scheme converges faster. This is a wall time, and this is a residual, maximum residual norm. So this is my waiting time. If I run conventional scheme, second order scheme, and third order hyperbolic scheme, I can get the third order solution fast. And that's impossible. No, but possible. The question is why? here's the iteration number versus number of nodes. The Hyperbolic Navier-Stokes second order scheme takes much less number of iterations. It has a better convergence rate. And in a way, we can understand this by we are having this consistent Jacobian. And for the conventional scheme, it relies on inconsistent Jacobian. So this is the conventional scheme. This is a little bit strange result, but on a fine read, it does require much less iterations. And here, this is the number of Gauss-Seidel linear suites, linear relaxation versus the number of nodes. Based on the fact that we don't have second derivatives, we can predict the behavior. This is slope 0.5 and this is slope 1. When you have second derivatives, this is what you expect. And it's not perfectly following, but the conventional scheme goes up. This number of relaxation goes up to reduce the residual by 1 over. But the hyperbolic scheme requires much less, and it has a completely different slope. And finally, the wall time versus number of nodes, you can also predict the slope should be 1.5 for first order system, and slope 2 for second derivatives. And for this one, they fall. The second order hyperbolic scheme is always faster and closely follow this 1.5. And the conventional scheme follows slope 2. And third order scheme is actually more expensive on coarse grid, but it will eventually beat this conventional scheme because they have different slopes. So by doing some smart programming or using many processors or whatever, you can take this data down, but it's very hard to change this slope. So it will eventually overtake. So that's what I mean by intrinsically more efficient.
Hiro?
Yeah.
Does it mean that the condition number of the Jacobian for the hyperbolic Fourier approach is much closer to 1 with respect to the conventional approach?
1 over h.
1 over h.
And second,
But it's a
you
better
have 1
number.
over h squared. It's much reduced.
Okay.
That's why this relaxation converges faster.
But the footprint of the Jacobian is the same. The non-zero element in Jacobian are the same.
Yeah. So much.
Sorry?
Stencil, the size of the stencil for third order is the same basically as for second order.
Of course, yes.
But also the position of the non-zero element in Jacobian is the same.
It's the same stencil, just
Okay.
basically quadratic fit versus linear fit.
Yeah.
And,
Okay, thank you.
there are cases where you need the augmentation. So
Okay.
So the first test case, I fixed the tolerance, reduced the order by the residual by 1 order. But like he says, typically the number of linear relaxation is fixed for practical reason. You don't want to spend too much time on relaxation. But my guess is it is still faster because the linear system is better relaxed, the condition one. So the second test case is cylinder. Now Gauss-Seidel linear relaxation is fixed, 100. That's it. So again, I have highly skewed triangular mesh. The outer domain is like 500 times diameter. That's really far. And these are pressure contours. The third order scheme gives much, much smoother solution in this one. And again, the viscous stress, you get highly oscillating skin friction. In a way, if you integrate this and to get the total drag, maybe error cancel, you may get a decent prediction. But the Hyperbolic Navier-Stokes, it gives so much smoother distributions. So here's the convergence. Let's focus on the wall time. The maximum residual, this is the maximum of L1 norm of each equation, n versus the wall time. We want to find a 3. The third order, I mean, all these 100 relaxations are not probably enough. This convergence is really awesome. But third order convergence a little bit faster, this one. If I define a mesh, for final mesh, I expect this converges much faster. So I constructed first and second, third implicit upwind finite-volume schemes for the Navier-Stokes. And when I say upwind, it's upwind for implicit and viscous and source. And these schemes give first, second, third order accurate viscous and heat fluxes and consistent Jacobian. And hyperbolic schemes are intrinsically more accurate and efficient than conventional scheme. And I'd like to just mention two remarks. Explicit time stepping is not possible because this is based on a hyperbolic formulation which is equivalent to the original in the steady state. But unsteady scheme can be constructed by implicit or space-time methods, and we have actually done this with algorithms. And also there is a recent work. I forgot the name. But if you choose the relaxation time carefully, you can actually achieve higher explicit time stepping scheme for time unsteady programs. Very delicate. But in that case, you lose the speed up factor. You have to live with all the h squared times. And also, the more memory is required, of course, because you have to solve more equations. And potentially 3 times more memory, or for implicit solver, somewhere between 3 and 9 times more memory required in 3. Because the residual is 3 times 5. The original Navier-Stokes equation has 5 equations. So 3 times 5. And the Jacobian block will be 3 times 5 times 3 times 5. So 9. The question is this the dead end? And I don't see it. There are future. So more extensive numerical experiments. I'm working on flat plate right now. I'd like to get these results soon. And the new approach to accurate computation of velocity gradients, I'm actually looking at a larger system that has velocity gradients as additional values. And higher number turbulent flow, those are the targets, but there are many others. And I don't stop here because attractive features encourage further study. But first of all, the smooth and accurate viscous stress heat flux on irregular mesh. This is very useful. The grid generation may become easier for complex geometries, and the grid adaptation can be performed inside boundary layer or area. And speed up the current state-of-the-art CFD code, second order, with high order accuracy. This sounds too good to be true. It can be faster and it can be high order. So, what happens to the myth? The myth number 1, busted. No, the arbitrary grid adaptation is possible inside boundary layer, whatever it is. If the viscous stress, the skin friction is the focus. And CFD myth number 2 is confirmed. Yes, there exists a third order scheme that is less expensive. You can get the third order solution faster than the code currently you are using. And the next biggest myth to be investigated will be this one. Extension to 3D is straightforward, as always. Thank you very much.
Boris and Jim, you found that when you have highly stretched grids over curved surfaces that the least squares breaks down. And because this is using least squares, is that going to cause a problem when you have a large gamma? Because now your reconstruction is failing in the near distance. Even though you've got these accurate gradients, your reconstruction itself that you're using to get the higher order scheme is failing.
Yeah, you're talking about high gamma, so it's not exactly in the limit of small mesh size. So it's you're saying, so it's what would be accuracy on a given grid with high gamma? I don't know. Like this cylinder grid probably had high gamma. I think so. It was very stretched grid toward this cylinder and the curvature, and bump grid also probably had high gamma. So it's
Yeah, I didn't anything special. But if there's a problem, then I can use this approximate mapping or there are techniques.
What is the aspect ratio near the
I don't remember, but
or like the skewness?
yeah, it's really random, but as high as 200.
Can you go back to that 3 by 5? No, right there near the end. You're talking about in the remarks. Yeah. So I'm trying to do the counting now. In 3 dimensions, I've got cow x, cow y, cow z, qx, qy, qz. So I've got 6 extra variables.
No, 9. Oh, it should be 14. 6 plus 3. Tau x, y, tau y, z.
Right.
Yeah,
Yeah. There's,
Oh, okay.
There's
Okay.
now the normal stresses, and then
Okay.
you've got your shear stresses.
that's
That
right.
would be
Xx, tau xy, tau xz.
right tau. And then y.
But
It's even more than that. Is it more than, is it 3?
12.
I just want to,
14. That's 3 times 5 is 15.
Okay.
Right. It's going to be 14 by 14 Jacobian block. If we use this system, I call this system system 14, but I'm looking at system 17 now. But,
I got some equations for you.
But I'd like to point out, if you use, for example, DG, second order DG requires 20 by 20 Jacobian, and third order DG 50 by 50.
I fully
Yeah.
support that you have to go and you have to look at it because I think there is probably another crazy idea that will make it work.
Yes,
And
yes.
And we just have to look. I mean, we can't.
Yes. Yeah, I'm trying actually looking at this Jacobian the way to reduce the storage.
I agree.
If you don't ask. I have another thing, important thing. Curved boundary. I'm actually investigating if this third order scheme requires curved elements. And I just don't see any reason that this scheme requires curved element. Because once this element is curved, this special property of third order scheme is gone. This is a very special property on linear elements. So we'll see.
Yeah, so it's high order extension, this curved boundary, that's a different topic.
Yeah.
But you ran the cylinder, which had a curved boundary.
I use a linear element, just a linear segment.
It's talking about P2 element, P3 element.
Yeah, the triangle with curved.
Oh, you don't know if you got curved interactions. Because you don't have.
I think I will lose third order like this.
I think you want it. You don't know the exact solution to the cylinder.
No.
So you don't know.
Have you got a method of manufacture solution?
Yeah, so that's why I'm doing that. Yeah.
When you're doing turbulent problems, what do you anticipate would be the impact of doing this upwinding for viscous stuff? What do you think it's going to be doing? Turbulent flows in terms of dissipation and things like that.
In terms of
Because it's making it kind of anisotropic in some sense, right? Whereas the traditional approach has been to do upwinding in the convective part, but then the diffusion part itself is more like diffusing kind of.
Oh yes. So upwind flux for hyperbolic viscous term is not actually upwind biased. Well, it's upwind biased, but this system represents an isotropic wave. So you upwind the left and right, you end up with a symmetric extensor.
As opposed to the convective where you have u plus or
Yeah,
minus a.
right.
So
So
that's
it is
not going to
right.
be symmetric, but just.
Yeah. But it doesn't have to be upwind. If you have a good scheme for implicit, whatever it is, you can apply that to this system.
Okay. Thank you very much.
here like forever. So please don't hesitate to come and ask whatever questions, crazy questions you have. He will give you crazy answers. Thank you.
And these guys' lawyers are going to come see you about
But Jamie and Adam just fired their build team.
They might hire you.
Yeah, that's right.
Okay.